Exponential decay is often described by a half-life. When we're working with something that is defined by a half-life, this formula can be helpful for our exponential model. In this formula, a sub 0 or a naught is the initial amount. We also have an x and a k up here in the exponent. And in this, x is the variable representing time, and k is the half-life, which is also in time, but it's a constant. So both of these are measures of time, and they both must be in the same units. So that means that if my half-life is given in years, my x variable that represents time must also represent time in years. A of x over here on the left-hand side tells us the amount remaining, right? So this calculates the amount remaining. We'll just say amount, or amount at time x. So if we look at this first example, we're looking at radon 222, which is an isotope of radon, and it has a half-life of 4 days. So right away we have a value of k, and we also have units for x and k. We'll say that k is equal to 4, and know that our time variable must be measured in days. Our question asks what percent of the initial amount, we'll deal with that in just a moment, of the amount of radon 222 released remains after 1 week. So our x, which is time, has got to represent 1 week. Since the units here are days, we're going to say that x equals 7. All right, now to handle the question about what percent of the initial amount, what we're going to do is say that a of x measures the percent remaining, or the percent at time x, so that our units are percent of the original amount instead of measuring this in grams or something, and that we start with 100% because we're talking about percent of the initial amount. So because we start with 100%, we'll just say that our initial amount is 100 in order to handle this percent type question. So that we get a of 7, that's the amount after 7 days, is equal to 100 times 1/2 to the power x, which is 4, divided by k, which is 7. Sorry, let's back that up just a second. X is 7 and k is 4 in this case. So the power is 7 over 4. All we need to do with this is plug it into a calculator because there is no variable to solve for. We want to know a of 7. So to put this in my calculator, I can enter it from left to right as long as I'm careful about parentheses. I'll say 100 times 0.5 to the power. Now I'm going to put my power 7/4 in parentheses. If I don't have that power 7 divided by 4 in parentheses, then order of operations is going to take over and cause me to raise 1/2 to the power 7 and then just divide the whole result by 4. So I put that power in parentheses as I was entering it into my calculator, and I get 29.7, so that it looks like what we have remaining is 29.7. Remember that our units here is percent, so this is 29.7% of the original amount. Let's check and see that this seems reasonable in the context. We started with 100% of the original amount. After 1 half-life, which in this case is 4 days, we should have half of that amount, which is 50%. After another half-life, which is another 4 days, we should be down to half again, which is now 25%. So after 8 days total, we're down to 25% of the initial amount. It makes sense that after 7 days, we would be down to not quite that low, somewhere between 50% and 25%. So our 29.7% seems quite reasonable in this context. In the next question, we are asked about a specific amount released. We're saying, what if we know that 5 milligrams were released? Then how much remains after 28 days? So in this case, we would say 5 milligrams, that's my A naught. That's my initial amount. And 28 days is giving me a value of X, telling me X is equal to 28. So I will say A of 28 is equal to A naught, which is 5, times 1/2 to the power 28, again divided by the half-life of 4. Now this time when I enter it into the calculator, I can simplify 28 over 4 just to make it a little easier to enter. Let's go with 5 times 0.5 to the power. 28 divided by 4 is 7, so I get 0.039 grams. Again, I can look at half-lives and make sure that this answer is reasonable. So I start with 5 grams. After 4 days, I'm down to 2.5 grams. After another 4 days, I'm down to 1.25 grams. After another 4 days, I'm down to 0.62 approximately. Then down to approximately 0.3, next down to approximately 0.15. So we've gone 1, 2, 3, 4, 5 half-lives. We need 2 more half-lives to make a total of 7 half-lives, which is that 28 days. So 2 more half-lives, we're down to 0.075 about. And then we can see that we're in the ballpark of this 0.039. Let's say around 0.038 would be about half of that 0.075. So we can see that this is reasonable just by going forward through as many half-lives as we need to go through in order to get to the number that we're interested in.